Hi, I'm Dr. Incognito. In this video, we're going to discuss the mean value theorem. The mean value theorem. So I'll begin by stating the theorem. The theorem says that if you have a nice function, if f of x is well behaved, if f of x is continuous on a closed interval, from A to B, and differentiable, that means that f prime exists, differentiable on the open interval A to B, then something nice happens. So if your function is well behaved on the interval from A to B, it has to be continuous, including at the endpoints. And it has to be differentiable just between the endpoints. It doesn't matter if the derivative exists or not at the endpoints. There could be a corner point, for example, at x equals a. That's okay. It has to be differentiable between a and b. So notice this one's a closed interval. The function does have to be continuous at the ends, but this one's an open interval. The function does not have to be differentiable at the ends, only in between. Then something nice happens. Then there will be a value c somewhere between a and b, such that f prime of c will equal f of b minus f of a over b minus a. So this is for some value c, for some c between a and b. Now let's look at this equation and see if we can recognize what these expressions represent. F of b minus f of a over b minus a, that represents the average rate of change of the function f of x on the interval a to b. So this one is average rate of change, and that's where the word mean comes from here in mean value theorem. This one's the average rate of change of the function f of x over the interval from a to b. Now f prime represents the instantaneous rate of change. So this is saying the instantaneous rate of change at some point c, somewhere between a and b, will equal the average rate of change of the function, the mean rate of change. So the instantaneous rate of change at this value will give you the mean rate of change, the mean value theorem. And there's a nice graphical representation. Suppose we have, here's a and here's b, and let's say that f of a is this height here, and let's say that f of b is this height here. And if I were to connect these 2 points with a nice function, continuous and differentiable, then maybe it'll look something like that. Then what the theorem is saying is, graphically, this quantity, the average rate of change of the function, is also the slope of this line right here, the slope of this secant line. It's f of b minus f of a, that's the rise, f of b minus f of a, divided by b minus a. That's the run, the rise over the run. So what the theorem is saying is that there's at least one place along the curve such that the slope of the tangent line is going to be the same as the slope of the secant line. So the tangent line and the secant line are going to be parallel in at least one place. So in order to determine where that occurs here, I'm going to just change my perspective a little bit by turning my head sideways so that I can think of this as being horizontal. And I'm going to look for the high spots and the low spots on the curve. So maybe there and maybe there. So if I draw the tangent lines to the curve at those 2 points, then I think we should find that they are parallel to the secant line. So I'll call this x value here, I'll call that one C1, and I'll call this x value here C2. The theorem says that the tangent line will be parallel to the secant line in at least one place. In my picture, there were two places, so I called them C1 and C2. So here, and the slope of the tangent line is f prime of C1, and in this case, the slope of the tangent line is f prime of C2. And these three things in this particular picture are all equal. The slope of these tangent lines is equal to the slope of the secant line. The most elementary application of this is if this axis were time and this axis were position, so that we have, say, a rectilinear motion situation, a motion along a straight line situation, like throwing something straight up in the air, then the average rate of change of the position function, this one here, would represent f of b minus f of a over b minus a, would represent the average rate of change of position. That would be what we call the average velocity. And f prime of c, f prime would be the instantaneous rate of change, so this would be the instantaneous velocity. So what in this context, what the mean value theorem is saying is that the instantaneous velocity at some point is equal to the average velocity. So if you're driving in your car and you're at a stoplight, and then you drive straight down the road to another stoplight, and you come to a stop, then if you look at your average speed between those 2 points, then your instantaneous speed had to agree with that in at least one place. Probably two. If you're at a light, you're waiting, you drive, you accelerate up to 40 miles an hour, and then you decelerate to a stop at the next light, your average speed might have been about 30 miles an hour, so you would have probably had instantaneous velocity 30 twice, once as you accelerated up to your maximum speed of 40, and then once again as you decelerated to a stop. But the theorem says that it will happen at least once, that your instantaneous velocity equals your average velocity. And let's look at a more mathematical example. Let's apply the theorem to the function f of x equals the natural logarithm of x on the interval from 1 to 5. The graph of the natural log curve looks like this. And here's x equals 1. The natural log of 1 is 0. And here's x equals 5. And there's the height natural log of 5, which is somewhere between 1 and 2. So the function is nice. It's continuous on the interval from 1 to 5, and it's also differentiable on the open interval 1 to 5. The derivative, of course, is 1 over x, and that exists for x between 1 and 5. The only problem with the derivative is that x equals 0, and we're safely away from 0. So our function does meet the conditions of the mean value theorem. The log of x is continuous on the closed interval from 1 to 5, and differentiable on the open interval from 1 to 5. So the mean value theorem applies to this function log x on this interval 1 to 5. So the derivative of the function should equal the average rate of change of the function on the interval. So the derivative of the function is 1 over x. That should equal f of b minus f of a over b minus a. In this case is log 5 minus log 1. The function is log x, b is 5, a is 1. The interval a to b, divided by 5 minus 1. And as I mentioned a moment ago, the log of 1 is 0, so this is the natural log of 5 divided by 4. So in other words, the derivative should equal the natural log of 5 divided by 4 in at least one place. And we can see that place. We draw the secant line, then the tangent line is parallel to it in at least one place. It looks like it's there somewhere between 2 and 3 according to my picture, but my picture might not be accurate. Let's see. 1 over x equals the natural log of 5 divided by 4. So that means, taking the reciprocal of both sides, that means x is 4 divided by the natural log of 5. And the natural log of 5 is less than 2. So this fraction is more than 2. So at least that part is right. I'm not exactly certain that this fraction is less than 3. You can check that on a calculator. According to my picture, it's between, the c value is between 2 and 3. I wouldn't trust the picture completely. The exact value is x equals 4 over the log of 5. And that's the value that we refer to here in the theorem as our c value. So c is the natural log of 4 divided, c would be 4 divided by the natural log of 5. So this is a look at the mean value theorem. Thank you for watching.